Hello, guys. Let's see.
Hi, teacher.
Hi, guys.
I sent you an email, and I don't know if you see.
Probably if I haven't responded, I haven't seen it yet. Let me see.
It is about the project.
Okay. So one thing that I'm going to do before the end of today is actually provide you with a Google form that you can use to fill up your project descriptions so I can start providing you feedback in a more like systemic fashion. Okay, so let's do it that way. Probably it's going to be for the best. So I'll do that. I'll probably do that while you guys are taking your quiz. So it's ready before the end of today's lecture. Okay, so let me see. We have 27 people in here. We have a good crowd. Okay, so just give me 1 second then so we can start. Okay, so here we go. See, about to turn on my camera and we can actually start working on this. Okay, so we can carry on with Doppler, which the last time that we were talking with you guys, we established that we made all the way to the continuous wave Doppler, right? And we were going to talk about the drawbacks of continuous wave Doppler and why is it that we don't use it. Okay, so let's carry on from here. And by the way, I saw that some of you started to work on the questionnaire too. Just again, remember that one is not graded in the sense that, it's not going to affect your GPA for this course or anything. So just go at it, for fun, for learning. Hopefully it will be beneficial for you guys and you can, ask questions during office hours or send it to the forums or whatnot. So the last time we were talking about continuous wave Doppler, we came to this defining equation, right, that tells us the amount of Doppler shift that we have when the ultrasound is interacting with a vessel where the blood is flowing at a speed of v, right? And we said that there were a couple of limitations that we were going to talk about today. One of them has to do with the spatial localization. The issue in here is that because you need to have your transmit and your receive beams interacting with each other, the region from which you're receiving signal can be relatively large. Your spatial resolution can be actually limited. Raster scanning your beams so that you can, move it around different locations or maybe create an image becomes again a cumbersome and very low resolution process. So that's probably not something that you want, eventually in the long run. I mean, you could have it, for not creating images, probably, but there is another reason that probably supersedes the limited spatial resolution argument, and basically paved the way to the pulse wave algorithms, which are the ones that we would commonly find implemented in scanners nowadays. The second limitation has to do with the fact that even if, you were to have that ability to intersect beams and to intersect them in very, very tiny and minuscule regions of space, which again, is quite debatable. It would be difficult in practice for you to accurately estimate the Doppler shift simply because of spectral broadening. Okay, so I don't know how familiar you're with that term. Like if I were to transmit a continuous wave, like a real continuous wave, right? Which in itself, it's debatable, right? You will have to have a very long signal, such that the Fourier transform is a true delta function, right? And even if it's really, really close to being a delta function, right? It can be super long and you sort of can see it in there. And then maybe what's happening is that, you know, you have a certain amount of blood flow. And in theory, maybe you're thinking, well, that delta is going to shift to a different location, right? So I can measure the new frequency and I can figure out what the shift was. And sounds relatively straightforward. But in practice, right? I mean, if I go to maybe forgetting about, you know, vessels and the cardiovascular system, even though you're probably knowledgeable enough that you would know the answer to this. But if you simply have a tube, right, like a pipe, and you have water, you know, or any other liquid flowing through it, would the fluid flow at the same velocity for every point inside the pipe?
No, it develops a velocity profile
Why?
because of the walls are rigid.
So, yes, sure.
I mean, viscosity takes place.
There are many, many reasons for it, right? And one of the reasons for it, because remember when we were talking about the wave equation, reflection and transmission, and, you know, continuity or like boundary conditions, and we said that normal component of the velocity has to hold, but the tangential we didn't care, right? Because it was like having two different lanes in a highway. So the medium one can be just running wild, and medium two, not quite so, right? And it really didn't matter. Well, you could probably argue the same argument here, right? And say that, I mean, why would that be the case? Because there are the walls of the pipe and then there's liquid flowing through it, and, you know, quite frankly, who cares? But exactly has to do with that. We are not dealing with two fluid media. We're dealing with a fluid embedded in a solid medium. And we are dealing with conditions in which we actually have, you know, dragging forces in between the walls of the pipe and the liquid that's flowing inside. So in this case, basically, right, again, because there are dragging forces, and there are many ways that these dragging forces, you know, come into play. But the idea is that the fluid cannot be, you know, like super quickly marching along, you know, while the walls of the pipe are rigid and stay in place. So you're going to have a profile in the velocity. You're going to have a different velocity at the center than the one that you have, you know, towards the inner diameter of your pipe. Now, the question would be, what type of profile would that be if you assume that, you know, the velocity at which the liquid is flowing is low enough, you know, low enough, and the diameter of the pipe, you know, is big enough. So if you go through all those underlying simplifying assumptions, what type of profile do you expect to observe in the velocity?
A parabolic one.
Correct, a parabolic one, right? So we are, like, in theory, and this is avoiding complicated things like turbulence, even in simple scenarios, right, where we have a pipe and we have a liquid flowing through it, you know, and the pipe is not like super tiny, but it's relatively big, you know, and the velocity is relatively low and everything like that. You still expect to have a distribution of velocities, not a single one. So what happens when you have a distribution of velocities, like in the context of, let's say, this Doppler estimation, right? You're sending ultrasound and it's interacting with a vessel where you don't have one velocity, but you have a whole bunch of velocities all coexisting together. What happens? What do you think would happen?
I don't know. Like I think we could have a general assumption that something like the mean of that profile of velocities will be measured.
Well, we can take a look at the formula that's right now on the slide, right? And it tells us that the Doppler shift that we are going to measure, or the Doppler shift that the signal is undergoing, is, you know, proportional to a whole bunch of things, and it's directly proportional to the value of v, which is the flow velocity. So what happens if I don't have one single v, but I have a whole bunch of values of v? What happens? What should happen?
We'll be detecting different Doppler shifts.
Correct. You will have a whole bunch of Doppler shifts, right? And just like there is a distribution, of how the actual values of the velocity occur, you know, at different points in the pipe. By the same token, you know, there would be a distribution of expected, you know, there would be a spread of values, and you should roughly, you know, easily be under ideal circumstances, of course, to predict how much of a broadening you should have, you know. But you're basically transmitting that, even if you transmit a purely sinusoidal signal, right? So you have literally a continuous wave, and the spectrum is a delta function. The spectrum of the signal that you're going to pick up, you know, when this very long harmonic signal interacts with the blood flowing, is going to be, you know, it's going to have a broadening. It's going to have a bandwidth. And at that point, right, you're not actually trying to solve the problem of locating a peak, you know, or to say a delta function, sorry, in the frequency axis, but you're trying to figure out which one is maybe the peak of that distribution, which in itself, you know, is a more challenging problem. It's not something that's impossible to do, of course, that would be ridiculous, but it's a more challenging one. Even if that were to be the case, right? One can probably argue that still, you know, it may be more difficult, but it shouldn't be impossible to do it. Now, the challenge comes also from the fact that even if that is the case, and you can locate the peak, ultrasound undergoes frequency-dependent attenuation when it propagates through tissues. That actually means that if you have a signal that has a, you know, peak at some number of megahertz, the high frequencies attenuate more, the low frequencies attenuate less, right? So if you're transmitting something that has, you know, a certain amount of power at, let's say, 4, 5, 6 megahertz, by the time that it propagates several centimeters and then comes back, it has lost a lot of energy from 6, some energy from 5, and, you know, a tiny bit of energy from 4. I'm exaggerating, but you get the point, right? So your spectrum doesn't have the same shape anymore. It's actually shifted towards the lower frequencies. Ultrasound, when it, you know, propagates in tissues, we experience a shift that will depend on many factors. It will depend on the bandwidth of the pulse that you're transmitting. It will also depend on the depth, of course, that you're propagating at. You know, the more depth you have, the more, you know, of a frequency shift you have. And also it will depend on the amount of attenuation, right? The more pronounced the attenuation, then the more of a shift you're going to have. And depending on the conditions, you know, that shift can be easily, you know, several hundreds of kilohertz. And I think we talked about this last time, but the Doppler shifts that you would typically encounter in ultrasound, you know, are actually in the kilohertz range. So you could actually have more of a frequency shift if you were to pay attention to the attenuation effects rather than the actual Doppler shift itself. So all of those things actually make it relatively impractical, you know, to use continuous wave Doppler for the estimation of the blood flow. So people took a fairly different approach, you know, many years ago, which is the use of pulse wave Doppler. Pulse wave Doppler operates under a very different set of assumptions, you know, a very different type of signal processing involved in here. So for pulse wave Doppler, right, and imagine the same scenario, right? You have a transducer. The transducer has a beam, right, that points into some direction. You have a vessel that points into another direction, right? So there's an angle in between the two. And you have particles that are flowing, which are your red blood cells, right? And in this case, there's like a one isolated particle, which is, you know, totally not what's going to happen, but you kind of get the point, right? So the idea in here is that unlike continuous wave Doppler, where you turn on your transducer, your transmitter, and it's just there, you know, on and on and on and on. And then there's the receiver receiving things, right? It's like, in this case, it's the same transducer that's doing the transmit and the receive. That's one thing. The second thing is that you just don't, you know, transmit and receive, and that's it. You transmit and receive echoes, right? And then you transmit at least a second time after, you know, a certain amount of time, and you receive the echoes again. And you're going to look at the echoes that you received from both transmissions. And you are going to try to figure out how much the signal shifted because the tissues were moving. That's the overall idea, okay? So imagine in this simple scenario, right? I have one particle that's moving, and it's going to be at a certain distance away from the transducer. So it's going to have an arrival time, certain arrival time. And then there's going to be a second pulse that's going to happen, you know, sometime later. And the particle is going to be either closer or farther away from the transducer because it moved, right? And that's going to change the arrival time of the echo. So you can look at both echoes, right? And say, okay, in the first one, it took whatever, right? 100 microseconds for the signal to arrive. In the second one, it took 101 microseconds for the signal to arrive. So there's a shift of 1 microsecond, and I can relate that, you know, to how much was the particle supposed to be moving. And because you have the amount of time that it took in between those two transmissions, you can translate that time into an actual velocity of the particle, right? Because the time you can change it to distance, right? And you know the time in between your two measurements, so you can calculate the velocity because it's just distance divided by time. Yes, David, I think you have a question.
Okay, so teacher, this is just a functional question to be clear. In
Sure.
order for me to send the second signal or the second pulse, I will have to wait the echo from the first signal, right? It can be
Correct.
done. Okay.
Correct. And that is actually a very valid question, because it's one that we're going to revisit later, you know, down the road in this very lecture, okay? Because you're absolutely right. I mean, you have to wait it out, right? I mean, you cannot just, you know, shoot your transducer like, again, like 1 femtosecond after, you know, you shot it the first time. Now, in this scenario that I was describing, say we have one particle, right? And we can see the arrival time of the echo, right? Which is something that, for example, people would care about in different modalities like ultrasonic tomography. You would care about things like the arrival time of the signal. But it turns out that in pulse echo ultrasound, right? And when you're imaging tissues, you don't have one particle that's moving and you get to see its arrival time. What you actually get to see is something like what's in the second, like the lower half of this slide, where you have, you know, echoes that just keep coming and coming. And then there's a second pulse and there's echoes that just keep coming and coming, right? So now if I were to ask you, you know, what's the shift in between, you know, these two signals? I mean, like maybe you can kind of see it, you know, because of course, I mean, you can look at the overall signal, you can compare it and say, well, it probably shifted this much, right? But you don't have things like, well, there was nothing and then there's signal, so this is one arrival time, there is nothing, then there's signal, so there is this second arrival time that you don't have. You actually have to look at both signals, compare them to one another to try to figure out how much the signals actually shifted. Okay, and that is one thing that, you know, fundamentally limits to some extent what you can do with pulse wave Doppler. Because ideally what you want is, tell me the amount of like time shift that you have for every point in your time axis, okay? Which actually corresponds to every point in depth. Because remember that, you know, time of arrival for ultrasound is equal to depth because of the pulse echo principle, right? Now, technically speaking, again, you know, if you're triggering your apparatus twice, right, as a separation of TPRF, right, where PRF is the acronym for pulse repetition frequency, so TPRF is a period of the pulse repetition frequency. There's going to be a delay, right, delta T. And you can probably very easily argue and convince yourself that delta T is going to be equal to 2 times Vy, Vy being the component of the velocity of the moving particles in the direction of the ultrasound beam. Okay, remember the beam was pointing that way, maybe the particles were moving in this direction. We call this X, this doesn't matter. We call this Y, this is the direction that we care about, right? That's the only one that we can pick up on. And you can probably very easily convince yourselves about that. Like if things are moving, like the beam is in this way and things are moving in this direction, then the time of arrival, I mean, yes, I know that you can say, well, it's not going to be the same, right? Because the Pythagorean theorem, yes, I know, but you know, to a very large extent, everything happens at the same depth. So you don't get to see a change in the time of arrival. In this direction, you get to see it, okay? So the delta T is going to be equal to that. And I'm reckoning that very likely you don't have any problems with that expression over there. But if any of you do, this is a good time to ask a question. Okay. Now, so in principle, right, again, nice and dandy. But the problem is, again, how do you do it in the case of, you know, ultrasonic pulses that continuously arrive? And this is an example of a simulated data set, right? So it's arbitrary units of voltage, because of course that's not 6,000 volts or something that was ridiculous. But this corresponds to actually simulating, you know, particles flowing, you know, in a given direction. And you can see that if you were to compare the signals on the left and on the right, yeah, they probably did shift relative to one another. But do you observe something else? Like, remember this nice cartoon that we had here, right? And it's like, okay, so what this guy did was he just copied and shifted the thing to the right.
There's a lot of noise.
There's a lot of noise. What do you mean by that?
Like I can't really see a signal clearly moving from like a time frequency shift or time shift.
So you're thinking that's because of noise?
Yeah, I mean, like the way I interpreted, these are two different signals. I can.
I mean, yeah, you can argue that they look like two different signals, right? I mean, for sure, that's not the same cartoon that we had before. The question is why? So your hypothesis is that, I don't know, like noise, maybe. I mean, sure, it can be. Well, remember that the signals that you receive from blood vessels are very, very weak. So that's maybe part of it, but not actually quite the picture. Yes.
Maybe the is the sum of all the frequency shifts that you receive in the path. So what I would have to do is maybe apply a correlation.
Let's stop at the first portion of the explanation, right? And that's basically what it is. And let's clean it up a little bit. I mean, the thing is, like you said, right? If every particle was moving at the same velocity, right? Then the only thing that happens is that, I mean, if the particles are moving, they're all moving together, right? So I transmit once and they generate one signal. Then by, you know, like raising my hand and claiming shift invariance, if the thing shifts a little bit more, right? Because everything moved, but everything moved together, then I get a second signal. It's just going to be a shifted version of the original one, right? Because I'm claiming shift invariance. But that's not the case in here, because not all the particles move at the same velocity. So maybe in the first snapshot, like, it's just imagine that, right? I mean, you have a camera, right? And there's a marathon and you're taking pictures. So click, you take a picture, and then you just try to keep up, and then click, you take a second picture. And it's not just going to be that, you know, it's the same people that just ran a little bit more, and now they're farther away from me, right? Because maybe one of them is going to be running faster than the others. So the separation in between them is not the same. It's a different arrangement, right? Simply again, because everybody's running at a different speed. So it's the same thing in here. The echoes are not bound to be the same, you know, even if, you know, we're under very idealized conditions, simply because not all the red blood cells are moving at the same speed. Is that the only reason why? Which I guess it would be, you know, going down the lines of the second part of what your classmate was saying. But is there any other reason why the signal will have to change like this? Come on, guys, don't be shy.
Is it possible that in the I mean, I'm not sure. Is it possible that in the way of coming back, like some other ships are generated?
What do you mean?
Like, of course, the signal is going to get down to the reflector, but as it is reflected, it also interacts with other particles that have already moved. So maybe those other particles also adapt the signals that you don't actually want.
You mean like multiple scattering between, you know, in between the reflectors?
Yeah.
It could be, but
yeah.
If I go to my simple example before, right? I mean, if I have a camera, right, and there's a race, and I take a picture, right, and at some point I'm going to see, you know, some runners, right? They're going to be within the field of view of my camera, and then I take a second picture, and then the second picture is just not going to be the first one shifted, right? Because again, what's happening is that some of them are going to be running faster, some of them are going to be, you know, running slower. And if I stay in the same place and I keep taking pictures, right, I'm pretty sure guaranteed that maybe like 2 or 3 seconds after, nothing is going to look quite the same, simply because of what? Simply because, you know, the first set of runners already left the field of view of my camera, and I have new runners coming in, right? It's just, you know, just simple reality. So you have a transducer beam, and there's a vessel, and red blood cells are flowing, you know, and at some point, some red blood cells are going to be here, but then they leave, like, again, this is the beam, they leave the beam, and some other particles are coming in. So the signal that's being generated is going to be generated by a set of particles that are continuously, you know, getting out of the field of view of your transducer. So whether you like it or not, the signal is going to change. You know, even if those guys were to be, you know, running at the same speed, eventually it's going to change because, you know, of the, maybe you have 100 red blood cells generating the first echo, then just because they're moving, you know, 3 of those red blood cells are not going to be in the picture anymore, and you're going to have maybe 3 new ones, you know, in slightly different locations. So the new echo is going to look slightly different than the previous one. And then you're going to have, you know, 3 more leaving out, you know, so it would be 6 of the originals are out, and so on and so forth, right? And you can extrapolate from there. So your signal in general is going to be continuously changing. So those 2 effects, you know, which probably the spread of values in the sound speed is going to be, you know, the one that's going to more severely hit you, are going to make your signal look like it's just changing, you know, from snap to snap. Now, it's not going to change so radically that there is no, you know, related features in between the 2, or they're going to be like massively different, but they can be significantly different. And this is what we know, or what we call signal decorrelation. So it basically means that, like, most of the signal kind of sort of is there, you know, but because, you know, things are moving at a different pace, particles are coming in and some are coming out, then the signal is not exactly the same, just shifted. And I agree. I mean, if you add noise to it, then that makes it even worse, right? So when we actually want to calculate, you know, the sound speed, there's a couple of solutions that we can envision. One of them is a fixed window algorithm, and the other one is a sliding or moving window algorithm. Both of these frameworks for calculating the sound speed when using Doppler, you know, are you know, reasonable and having explored in the literature. And the idea behind the fixed window algorithm is that you place, like, you have your echoes, right? And you analyze data for a certain segment. So there is one location for the window and there's one width for the window. And then you have a second pulse, right? You transmit a second time and you got your echoes. And you look at data which is located within the same, you know, time limits, like the same starting time and the same ending time as you did with your first set of echoes. You look at the data, you compare them with one another, and you try to figure out, you know, how much the signal shifted. And you can see in here that, yeah, sure, of course, right? I mean, I have, you know, some echoes, and then I look underneath and, oh, it looks like it's slightly shifted to the right, you know, and I can sort of infer, you know, how much the signal shifted. Again, how exactly do we do that? We'll talk about that in just a little bit. The second set of algorithms, the sliding or moving window algorithms, sort of kind of almost do the same, but not really, right? You have a portion of the data in your first set of echoes, for example, and then what you're going to do is you're going to grab that portion of your data and you're going to slide it over, you know, the second set of echoes, trying to find a location at which the correlation in between, you know, that window and the gated portion of the second set of echoes is the highest. Okay, which, like you said, Brendo, I think he said that hints of, you know, applying a correlation, right, in between the signals, which is true. It's one of the ways that you can, you know, sort of predict, you know, the similarity in between two signals, right? That's one way to do it. So which one do you think would be more consistent in between these 2 types of algorithms?
The second one, maybe, because we
It
are
kind of
looking.
sounds like it, right?
I
Exactly.
mean,
Why,
we are
why do you
looking
think that
for
would
the highest correlationship. The second one sounds like the way to go, you know.
Right, exactly. I mean, it sounds like it would be the way. But the thing is, oddly enough, you know, when you go to the literature, it's the fixed window algorithms, the ones that, you know, have been implemented in scanners and remain to be implemented in scanners in spite of, you know, the sliding window ones looking like, you know, the ones that should be the preferred ones. And we'll talk about the reasons why in a little bit, actually in a lot bit more, but you can get the point. So let's talk about, you know, fixed window algorithms first. And probably, you know, the simplest, or I don't have to call it simplest, but, you know, one of the most widespread algorithms that you can find in the literature would be the phase shift algorithm. Okay, and we're going to look at it. We're going to analyze it and try to figure out, you know, strengths and weaknesses of the algorithm itself. So the idea in here again is that you're going to transmit, and I'm going to say at least 2 pulses. Okay, so you're going to transmit your ultrasound signal at least twice. You can do it more than twice, okay, but you need at least twice. And if you were to do something like that, then you are going to have a signal that you're going to receive, you know, after a certain amount of time, right? And corresponding specifically to the signal that you're going to obtain, so that will be the T in parentheses, but it corresponds also to the signal that you are going to observe after the ith transmission, right? And that's going to be, you know, in principle, the signal, right? The RS naught, right? At time T minus ITS, right? So the idea in here is you have, you know, something that you're transmitting, right? And you're going to get some echoes. Like if the only thing that's happening in here is that things are moving at a constant speed, right? What should be happening, right, ideally again, would be that if you wait an amount of time, you know, that is given by equivalently the TPRF, right? Then what's going to happen is that because things are flowing at the speed of c, and remember I told you guys before, everybody understands this equation over here that was like 10 minutes ago? Dandy, because if you understood that, then you understand this, right? The time that is going to be delayed is going to be I, which is the number of, you know, the echo. So it's the first echo, then it would be 1 time that. If it's the second time that you transmit after the initial one, right, then it would be twice that much, and so on and so forth. Multiply by TS, where TS is there, right? 2V divided by C, multiplied by TPRF, where the subscript B sub Y, the sub Y has been dropped simply to make this more palatable, right? So otherwise it's just a boredom. So now that's roughly what we should be getting, right? So let's assume a narrowband signal, and I actually heavily edited, you know, the math in this derivation, and sometimes I quite regret it. I think, you know, one of these days I'm going to give you maybe the full derivation, so you can have, you know, the nitty-gritty step-by-step list of things in here, and you can figure it out on your own. But I'm editing this for the sake of time, right? So if we assume a narrowband signal, right, and there's many things that carry on with that, that basically means that we are going to have a GI of T, which is an amplitude modulation term, and basically we're going to have an e to the j 2 pi f naught, blah 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 blah, meaning I'm going to have a frequency modulation happening at a given frequency, right? So I'm going to have a signal that's frequency modulated, right? Amplitude modulation and frequency modulation, and the frequency modulation more than anything here, it would be having a carrier frequency, right? So that's basically the assumption in here. So we have a dominant frequency. And that's, by the way, and parenthetically speaking, the reason why you in Doppler imaging are going to use long pulses, even if you operate in pulse wave mode. Okay. Now, long pulses doesn't mean that you're going to transmit 20 cycles of the fundamental signal, but it's roughly something like you're going to transmit, 6, 8 cycles. I mean, you still make it long, just so you know. Okay. Now, the argument of that exponential shouldn't be that difficult to understand, right? It basically has 3 components. The first one is 2 pi f naught times alpha times t, right? Where alpha is c minus v divided by c plus, v, and I forgot to drop the sub index y in here, but you kind of get the point. So what does that correspond to? That portion of the signal, what does that correspond to? The e to the j 2 pi f naught times alpha times t, what does that correspond to?
It looks like the attenuation coefficient.
Oh, no, it's not totally. Look at the equation. Have we seen this, at some more portion of our lectures so far? We have, right? Last lecture. So what would be f naught times alpha?
The Doppler shift.
Correct. No, it's the Doppler frequency actually.
Oh,
right. The Doppler shift would be the difference in between alpha f naught and f naught, right?
Mm-hmm.
But yeah, it's the Doppler frequency. Correct. So basically, it's saying that, okay, so I transmitted something at f naught, and I'm going to see it oscillating. Like the signal is still going to be oscillating. It will have, an amplitude modulation component, which is the envelope of the overall signal, right? That's relatively easy to understand. And then the oscillations themselves are going to be not at f naught, but because things are moving, then it's going to be at, alpha f naught, which is the Doppler frequency. Now you have the second component, which is 2 pi f naught times 2 times v divided by c times I t PRF. Was that?
That's not the delay.
Correct. That's the change in the phase of the signal because something is moving, right? And see that part is the one that encodes the I, right? It's basically the only part of the signal, in a sense, right? I mean, of course, there's the G sub I thing, but it's the only part of the signal in itself that encodes or carries the information about the fact that I fired my ultrasound transducer for an ith time, right? So that portion in there, again, if you have something like E, J, 2 pi, F naught times something, basically it's telling you that something is the phase, right, of something that's resonating at a frequency of f naught, right? So exactly, it's a phase shift. I mean, it's basically a time shift, that's encoded as a phase shift in there. And then you have the 2d naught divided by c, which is just the, the initial arrival time, which is a constant for everything. It doesn't depend on t, it doesn't depend on I, right? So it's just a constant thing that's there because, I mean, signal starts at a given time, right? So there's an initial phase, and that sort of makes sense, of course. I mean, every sinusoidal signal would have to have an initial phase, right? So this is basically saying that you have a signal that has an initial phase, right, which is given by the last term, that it can also shift if the things are moving, right? And that would be encoded in the second term. And then the first term is just telling you that the frequency itself is going to be shifted if there is movement in the medium, right, by the Doppler effect. Okay, so again, equations are nice, but the true ability should be to look at them and really digest them and to be like, okay, this means this means that, and so on and so forth, right? Now you can demodulate this to baseband, which is probably quite kind of irrelevant, but most of the times, remember, we have baseband signal. So we can have, and we just re-encode this to be, S sub I of t, which would be, the amplitude, then the G sub I, which is just the envelope of the echoes, and then the E to the blah, and there's a factor of alpha minus 1, because in order to demodulate it, you multiply it by E to the minus J to pi F naught times T, right? So that goes into the alpha minus 1. So I guess at that point, yes, you can say that. Now you can say that the term alpha minus 1 times T encodes the frequency Doppler shift, right? Because now it would be the shift. Now, the thing in here, right, and this is probably a fundamental moment that can be super complicated for people studying these things for the first time. So this is the moment where you actually ask tons of questions, right? But anyway, so the time t is referred to the moment that you transmit, right, the ultrasound wave. So can you see it? I mean, technically speaking, what I'm doing is, I mean, there is really a time 0, and then I transmit, right? And there's something, and then there's a dead time, and I transmit a second time, so I have some echo. So if I really think about the t-axis, right, the true t-axis, it's a continuous thing, where, I have my echoes from the first transmission are in here, the ones from the second transmission occur farther to the right, for the next transmission further to the right, and so on and so forth, right? But what we do here is we refer the t to the moment of transmission of the ith pulse, right? So what we do is we actually look at this thing, right? We take a look at the signal that we have in here, and we can call this, the S of t of I, which is equal again to some amplitude and some enveloping. And notice how we're actually rewriting the echo, right, to be a function of I rather than being a function of time. So we're actually looking at the data, at a fixed value of t. So now I'm going to fix t, right? I'm not going to fix I, which I did before, but I fix t. Okay. And if I do something like that, right, then the expression can be written as a function of time in what we call the slow time domain. So we actually don't use I anymore, but we use a variable that we call tau, which is actually going to be equal to I times TPRF. And we come to that second expression over there, right? And there's phi c, right? Phi c, when you really think about it, would incorporate the 2d divided by 2d naught divided by c, and also the alpha minus 1, multiplied by t, because those two terms are independent of tau, right? For all that tau is involved, they really don't matter, right? For tau, they're constants. So we actually write this down in a way, that is given for a fixed value of t and a variable value of tau. Do you guys understand this? And if you don't,
No.
questions. Okay, what don't you understand? Hopefully you can elaborate a little bit more than I understand,
Yeah.
right? But so what is it that you don't understand?
Like okay, I understand that the in the first formula we are just like looking at a different fighting positions, and then we are looking at how a fighting position moves across time, but I don't understand like the last formula. How do we pass from that?
Oh, from the second to the first, but you guys do understand the second and the first? I guess that would be super important that you do. Do you understand the first and the second? We can do one thing, right? I mean, can you raise your hands if you understood the first and the second?
I mean,
Or let's do it
5,
this other way. Can you raise
yeah.
your hand if you didn't understand the first and the second, right? So I mean, if the answer is nobody understood, then that would be simpler to check.
Okay. The
Be
second I get.
courageous, right? That's fine. It's just, I mean, if you didn't, you didn't, right? There you go. Okay, cool. So I mean, have like most people didn't, if anything, right? And that's okay. I mean, why should you, right? So let's talk about this in more detail. Okay, now we're going to rely on my awesome, whiteboard drawing abilities, which are not that awesome. So imagine that, we have, and again, don't trash my, drawing ability. I mean, I'm just, putting gibberish in here. I mean, there is some signal, right? And this would be the time axis. And this would be for, I equal to 0, right? Something. So there is, and this would be some signaling here, right? So some Si of t, right? Which, I mean, again, is what it is, right? I mean, it has some enveloping and it has some oscillations and it has all the components that we were talking about before. Some nonsense, right? Now, if I transmit a second time, like this, right? And this would be for, I equal to 1, right? I mean, I really don't know. I mean, I will get something, right? And I'm just, again, this is just gibberish. It really doesn't matter, right? You get something else. And you transmit a third time, right? So you will have this as a function of time. And, this would be for I equal to 2. And again, you get some gibberish again, right? Like, really, I mean, whatever. I'm just, so again, a few things, right? I mean, notice how every time that I have my time axis, right? It always starts at 0, but of course that doesn't make any sense in the sense that, I mean, of course, the time of arrival of the second set of echoes has to happen, from a philosophical point of view, right? Has to happen after, the first set of echoes vanished. Because I kind of, to begin with, had to fire the transducer, like after the fact. So you do understand that, but we are actually always referring the t-axis down to the moment after I fire my transducer for the ith time, right? And now, when you think about this, and this is a very interesting thing here, right? I mean, for people in the radar community, which are the ones that introduced this concept, you have, here the time variable, and they called it the fast time. The reason for this is, this is like in our case, it would be a signal, that maybe, has a bandwidth of, I don't know, like 20 megahertz, something, right? I'm talking bandwidth, I'm not talking center frequency. So you have to, sample it at least at 40 megahertz, right? So that's a fast sampling frequency. So the signal is happening at a really fast time. It's oscillating, at megahertz. In comparison, how often do I pulse my transducer again? Do you guys know? Do you remember? Like, how often do I pulse it? Like, roughly, what's the ballpark? In which type of, like, which order of magnitude are we talking about?
Microseconds, I guess.
That would be generous, actually, right? Because if it's microseconds, right? I mean, actually, my signal is oscillating. If it's in the range of megahertz, and it's oscillating in the microsecond range, right?
Mm-hmm.
So actually, that's very generous of you, but it's actually milliseconds. For reasons that will be probably more apparent afterwards. So the PRF actually ranges typically, in, again, the range of the kilohertz. So we're actually shooting out the transducer, over and over, much slower, right, than the megahertz that I'm using to sample the signals in the time domain. So in the I domain, right, I'm actually grabbing, it's like grabbing a sample. It's just that each one of my samples is a waveform, right? So I have my sample at my first, shooting, and then at the second shooting, and then at the first shooting, each one of those being, waveforms, right? So I'm sampling also, but I'm sampling at a very low pace, And that's why this is called slow time. Because interestingly enough, what you have is two time domains, okay? And that's one thing to remember. Now, imagine that I were to do something like this, right? Okay, great. Instead of looking, because I can, right? I mean, I have my signals graphed in a way that you understand that. Like for each transmission, I have a waveform that is changing across the t direction. But I can also go to a fixed time, right? Draw a line and actually create a plot of how my signal is going to change as a function of I. And I will have, you know, like in here, I will have a sample at I equal to 0. In here, I will have a sample at I equal to 1. In here, I will have a sample at I equal to 2, and probably so on and so forth, you know, as long as, you know, there is a so on and so forth going down, right? Can you envision that?
Yeah.
Yeah.
Okay.
Yeah.
Imagine that nothing is moving, right? I don't know, I just grab my transducer and I place it on top of a gelatin phantom. What would that plot look like? This plot over here. If nothing is moving, how would it look like?
All the discrete points will be on the y-axis 0, I guess.
Would they be 0?
Will be a
Or at least
constant.
they'll be the same among all the I
Correct.
measurements.
There will be a constant, right? So it will a flat line, completely flat line if nothing is moving, right? Because it's the same thing over, I'm sampling the same signal over and over again. If things are moving, right, I would get to see that that curve starts to change. Okay, and that is the way that this analysis will operate at. When we do Doppler imaging, the fundamental direction in which we're tracking movement is the slow time domain. Now, again, remember that we think, oh, we have time in the horizontal domain. And that's actually kind of cheating, right? Because, I mean, we never have a continuous time signal, right? Especially nowadays with the electronics we have, everything is a discrete time. We have a sample and hold circuit, right? We have an A to D card. So you have a voltage and we get sample 1, sample 2, sample 3, but we're probably sampling it at, you know, 1 gigahertz or something. So we get to see it very nicely changing. But again, we call it time, right? Which is nonsensical because we actually have samples, right? I mean, if we were to actually plot this is at this, you know, one period of the sampling frequency, one sample, the second one sample, third one sample, so on and so forth. So if we are calling this one T, right, which is not T, it's actually something like J times, you know, sampling period, right? But still, we called it something like, we called it T, and we made it a continuous variable, right? So what's stopping us from saying, well, why don't I call my slow time axis, I'm going to call it tau, you know, which is going to be equal to I times TPRF, right? And because why not, right? So if I'm doing the same thing for the fast time, then why should I treat the slow time differently, right? That's racist. And it's easy to see why, of course. You know, in the fast time, you have a whole bunch of samples. In the slow time, you have a few, right? And that's probably why we're always reminded that at the slow time, you know, it's discrete sampling. But the fast time is discrete sampling too, right? So the heck. So we call this tau. And we have a signal, you know, versus tau, which is the slow time. Okay? And what we're talking about right now is that if we can somehow infer or relate how that signal as a function of tau is changing, because we already established, you know, that if I analyze things in the fast time domain, I don't know, the signal is continuously changing, right? But if I go to the slow time domain, like I don't look at my signal from the fast, but the slow time domain, I look at traces of tau. If nothing is moving, I see a constant. If something is moving, then my signal changes. So the motion, I can clearly see it when I look at things across tau, and I don't see anything when I look at things across t. Okay? So that's why we're analyzing things across tau. So I can actually ask you again, I suppose, can people who don't understand the first or the second equations again in this slide, raise your hands again. Awesome. That's the magic of, you know, the whiteboard. I mean, if we were actually, you know, at the university, we'll be having so much fun with you guys going to the whiteboard and doing this for me. That would be awesome. Anyway, so that's what it is. Now, the big question, of course, is, okay, fine. Like, you convinced me, right? If things are moving, right, then I can see it in that, you know, trace that you showed in there. But how? You know, how do I relate the shape of that curve? And right, that's kind of tricky, right? I don't know. I mean, it's complicated, right? In general, I mean, the signal is moving, so the things may be moving, but it may not be tractable to determine how the shape of that thing is going to change. But when you really think about it, right, and you claim, like, if you claim that the signal is truly narrowband, right? Do you remember when we were talking about the far field expansions, right? And we said, like, in general, when you're analyzing signals, right, you have the dominant component analysis, right? So basically means that if you have a signal that has a very, very slow changing component, and you have a component that's changing super fast, right? If you want to look at, like, if you want to analyze the changes in the signal, you focus your attention on the fast changing one rather than the slow one, right? And a very direct corollary of this is that if you want to figure out what the phase of a signal that has a very slowly changing, you know, enveloping, right, with a very fast oscillating component, then the phase of the signal is going to be very much related or linked to the change of that highly changing oscillatory component. So basically what we're saying in here is, okay, I don't know really how the shape of the curve is going to change, but I know one thing. If I look at the change in the phase of the signal, okay, change in the phase of the signal, what's going to be the phase of that signal in here? I already said that, well, A is a constant, G, I assume that it's slowly moving. So the phase of that thing is going to be, you know, whatever is in there, right? The 2 pi f naught times v, 2 times v divided by c times tau minus phi sub c, right? Phi sub c. So when I take the derivative of this with respect to tau, right? Then hopefully you can easily understand that the part that's phi or phi of c, that goes away, right? Because it doesn't depend on tau. The only part that depends on tau is the first part of that phase. And again, the phase of g sub t of tau is irrelevant because we're already assuming, you know, that that's a slowly changing signal, and the main carrier of the phase is going to be the exponential, right? Because we claimed that it was going to be narrowband, so who cares, right? Okay, so we take the derivative, and again, right, I mean, it's the j goes out, and then there's the 2 pi, the f naught, the 2v, and the c, right? I mean, that's just straightforward derivation of the phase of that exponential, or the argument of that complex exponential, right? So that should be the derivative with respect to tau of phi, right? Of the phase of the signal. And in there, you can see something really, really interesting. If you would be able to compute the change in phase of the signal in between, you know, like different values of tau, right? If you were to be able to calculate that function, then you could actually make it exactly equal to number, because you know 4 pi, right? That's just a constant. You know C and you know F naught. The only thing that you don't know is V. So if somebody were to tell you, this is the function differential with respect to tau of phi, where phi is the phase of, you know, the signal, then you could directly get V. Okay. Do you guys follow? So
I mean,
can you give me a thumbs up if you follow, and if not, then I know that you don't.
the derivation of phi, like you said, we underestimate the amplitude and the G, but just derivate E, right? And the first component of E.
So again, we're basically assuming that the only thing that contributes to the phase would be the exponential, the complex exponential.
Mm-hmm.
And when you have a complex exponential, it's just a sinusoidal, right? So if you want to know the
Yes.
phase of the sinusoidal, it's just everything that comes together with J, right? That's e to the minus J or e to the J times theta, right?
Oh, okay, okay.
And that will be cosine of theta, sine theta. So you know that's
Right.
the phase.
You're
It's an
driving inside,
instantaneous
right?
phase, right? Because it's changing. In this case, it changes as a function of tau, right? Which again makes sense, right? For every different value of tau, you have a different phase, right? The signal is shifting. So it's not the same. I mean, if it's the same, then we won't see anything, right?
Mm-hmm. Yes, I got it.
Mm-hmm. So we're basically just saying, if we were to have the derivative of that variable with respect to tau, we could actually directly relate it to the value of V. V as some, you know, scaling factor of 4 pi divided by C multiplied by F naught, right? But we can directly get it. Do you guys get it? There's one thumbs up. So now, quite honestly, who didn't get it? Raise your hand. I see thumbs ups, you know, and so did anybody not get it? Ask questions now, right? I'm here. None of your friends are going to be annoyed if you ask a question and, you know, you didn't get it. Ask questions if you don't get it, guys. I mean, don't make your education into a MOOC, right? Just like, I'll watch the video later and I'll figure it out. That's crap. I mean, your parents didn't pay for MOOCs, right? Or yourselves. You're paying for courses where you have your instructors addressing questions. Otherwise, just read a textbook or Wikipedia and we'll issue a diploma after 5 years. That's not what you want. Okay, awesome. I'm going to completely assume that you totally got it. You know, we're virtually high-fiving right now. So, of course, the question is, okay, that's awesome. How on earth do I calculate the derivative of phi with respect to tau, right? Because it's like, I don't know. I mean, how do I have phi to begin with? Do you know how do we have phi to begin with? Do you know? Does anybody know?
Yeah.
How do you have it?
It is the component that's inside the exponential expression.
Oh yeah, no, I know. But in practice, how do you measure it?
Oh.
You remember, guys, that I told you that scanners do a very, very nice thing for you, right? And this is something that is not unintended. It's something that's inherited from, you know, the radar community. Remember that ultrasound for a very long time, the only thing that they did was shamelessly, copy everything that, somebody else proposed, completely shameless. So scanners actually digitize not the radio frequency data directly, but the IQ data, right? And I know that we talked about this, right? When you have a signal that's modulated at a carrier frequency, right? It will have a certain bandwidth, but just because it's modulated, you already know that, the maximum frequency within the band is actually, that you're wasting bandwidth, let's say it that way, right? Because all the information, is contained within the bandwidth of the signal, but because it's modulated, the maximum frequency is larger than the actual width of the region in frequency domain where your signal is different than 0, right? So one thing that people would do when you have modulated signals is you demodulate it. So you basically transport this back to baseband, meaning you have it, centered around 0 hertz. So if you had, for example, a signal, right, that would be 1 kilohertz in bandwidth, but it has a carrier frequency of 100 megahertz, right? Just to give a ridiculous example, you could either digitize it at 200, I said 100 megahertz, right? So 200 megahertz, right? Or you could bring it to baseband, right? And because it only has a 1 kilohertz bandwidth, hopefully I'm remembering the numbers correctly, then you only need to have, because it's 1, maybe it's, centered at 0, so you have half a kilohertz on both ends, then you can digitize it at 1 kilohertz and get it over with, right? So that's the reason why people were smart and wise enough many years ago to say, I'm not going to, deal with this junk. I'm not going to digitize the original signal. I bring it to baseband so I can digitize it at a lower sampling frequency, right? And there is a very, very nice thing about this. When people do that, right, what they would do is to create a complex function, right? Because remember, when you're bringing that component down to baseband, your signal doesn't have a symmetric spectrum anymore. If your signal doesn't have a symmetric spectrum, then your DSP teachers already showed you that the signal has to be complex.
Yeah.
Right? So you transform the real signal into a complex signal. And it kind of sounds like a bummer, right? Because now instead of having 1 channel, you have 2 channels. The real component and the imaginary component of the analytical signal. And we talked about this again when we were talking about the envelope of the data, right? And I told you, scanners give you the I and the Q components. So you can calculate the envelope by simply saying square root of I squared plus Q squared. So that makes it easy, right? The other thing that comes in very handily is that because you already have those 2 components, then the phase is simply the arctangent of the imaginary component divided by the real component. So the beauty of this is that you don't have to do anything. Okay, the way that scanners sample the data, right? You could think, crap, now I have to calculate the phase of the signal. Well, you kind of don't have to, because you already have everything you need. You already have the real and the imaginary components of an analytical representation, which means that the phase is super straightforward to calculate. Now, you don't need the phase, you need the derivative with respect of tau, right? And that you can do with the chain rule, right? You have the derivative with respect of tau of the arctangent of y divided by x. And there it is in all its glory, right? It would be x times derivative of y minus y derivative of x divided by x to the square plus y to the square. So if you were to actually know what the derivative of x and y are with respect to tau, then you can know what the derivative of tau with respect to, sorry, derivative of phi with respect to tau is. Okay?
Yeah.
Sorry,
So,
yes, questions.
So my question is, if I understood right, like all the ultrasound scanners do this demodulation step like right down from fabric?
Yep.
Oh, that's nice.
Yeah. I know. Now, that's great, right? But in practice, right, of course, you don't have the slow time sampled continuously, right? Again, because it's like I fire it at one time and then the next time and the next time. So we don't have the actual derivative of x and derivative of y with respect to tau. But what we do at this point is we can actually do finite differences, right? So the derivative of y, I can calculate it as y, you know, at the firing sub I minus the y at the firing sub I minus 1, right? So I look at the values of y, and I look at the current, and I look at the previous, and I subtract them, right? And that's it. And the derivative of x with respect to tau, I can do exactly the same thing. And if I do that, then my derivative of 5 with respect to tau is approximately what you have in there, right? So you need the sample of x and samples of y, both at the current firing and also at the previous firing, right? And that's it. That's everything that you need. So let's think about this, you know, in a little bit more detail, going back again to the whiteboard. The whiteboard is awesome. So goodbye, cool drawing. Okay, so basically, right, let's imagine now that we have, like, this would be, you know, time. And again, my drawing abilities are preposterous, okay? So I'm doing my best in here. So this would maybe be for I equal to 0. And let's say that this is for I equal to 1, right? And I'm just being a super nice guy here and saying like, okay, blah, right? Like, I don't know. I mean, I probably drew it horribly, but you kind of get the point. Like if I ask you, right, what's the time shift, you know, at this value of tau? What's the time shift?
Quarter of a wavelength.
Quarter of a wavelength, right? So what's the phase shift? The phase shift would be pi divided by 4, right?
Yeah.
By 2, sorry, by 2.
Mm-hmm.
There's a quarter of a wavelength. And
increase.
And I told you guys again, right? I mean, you many times have equations, right? But the idea is to clearly understand where the equations are coming from in trying to relate them. And don't ever, hopefully, go to lectures like at any point in your life, right? Because that would blow where somebody randomly asks you to believe, you know, that indeed, you know, this should be, you know, the thing, and you're meant to suck it up. Really think about it, right? You have the change in phase with respect to transmissions, right? So that would be what? That would be, like in this case, we're saying it's pi over 2, right? Mm-hmm. And that pi over 2 is a fraction of a period of 2 pi, right? So you can have it in there, and that's the amount of, you know, let's call it, if you do it in that way, right, then that would be the fraction of the period that is shifted. And then if you multiply it by 1 divided by f naught, that becomes a fraction of the period in time that it changes, right? And if you multiply it by c, you convert that to what? The distance, right, that the particles had to be moving so that there was a change in time of this amount, right, or response to a distance that it traveled, right? Mm-hmm. And if you divide it by, we're saying differential with respect to tau, that is, we divided by the time that we took to fire the first and the second one in between, then you convert it to what? You convert it to the velocity. And that's simply what the algorithm is doing. So as you can see, many times, actually there's a famous book, you know, by, the author is Jørgen Jensen. He's a Danish researcher, right? So we had Hans Christian Andersen coming from Denmark, and I guess we had Jørgen Jensen like many centuries afterwards. And he has this, you know, like defining book on, you know, Doppler. And I remember when I got my copy of the book, because it was out of print for a very long time. And it's awesome. It's uber complicated though, you know. And I always remember reading the derivation for the phase shift algorithm, which was like tons of equations, which is what I was telling you guys. I mean, I sometimes I debate myself, should I just give you all the equations? And maybe my concern is that sometimes that takes away from the beauty of the intuition, right? And when you really think about it, many times defining equations have such a clear and meaningful explanation that when you think about it that way, it's actually it actually makes the math more palatable because you kind of know where you're going. Okay, so hopefully you kind of understand, and you know, hopefully the approach is correct in the sense that sometimes I like to have you force yourselves to think about the math first. But where you think about the intuition first or the math first, you know, it's up to you guys. Don't ever just, you know, go through math because it kind of says so, and here's one equation. I don't even think it makes sense, but that's what it comes out, so it has to be. Don't do that. And don't go the lazy route either of saying, it's like I intuitively think it's this and that's it. You know, both things have to match because you're engineers, right? And that's a big word. Okay, so just keep that in mind. Anyway, so this is not the only way, of course, that you can relate those terms. You know, I'm listening here. I mean, for other courses, like more advanced courses, I have, you know, list of like full derivations of, you know, the many ways that you can come up to alternative formulations. And here's another one, you know, that I mean, I could talk about it at some point, maybe where it actually comes from. I guess in a sense, it would be relevant, but it's basically just there to tell you this is not the only way. There are many ways that you can work your way out of the phase shift problem. But in any formulation, it involves looking at the phase of the signal for 2 consecutive transmissions. See how much the phase shifted, and translate that into a time shift that would be translated into a distance that would be translated into a velocity, and that would be, you know, related one-to-one to the velocity that the particles are moving. So we still have 5 more minutes, so that's okay. So a few things about this, right? That we're going to go into more depth afterwards. We said that the phase shift was pi over 2, right? Is that the only acceptable answer?
Do you mean like 2 pi minus pi over 2?
2 pi plus, or 2 pi plus pi over 2. It could have been an answer too, right? 4 pi, 6 pi, right? And really think about it. We are actually, like what we're doing is, we're looking at, like if I go up, and you remember I said fixed window and moving window, right? How big is my window?
Right.
How wide is my window? What's the width? That I'm using for the phase shift algorithm. How wide is my window? It's just one sample, right? I mean, the only thing that I do is I look at one sample, right? In fast time. And I look at, you know, the sample at the same time, fast time in the next transmission. And I compare the phase that the signal has at those 2 points. That's the only thing that I do.
Yeah.
Right? So that's amazing, because it means that technically speaking, you know, like from the point of view of the signal processing, post-wave Doppler, you know, has a perfect, you know, spatial resolution. You only need one sample. You don't need to have all things to calculate anything. It's just one sample. That's awesome. Like theoretically, of course. That being said, what happens, right, if my signal shifts more than one period of the sinusoidal from one pulse to another.
It can't be seen because it would be out of
Correct.
the window.
Correct. Because if it moved, imagine that it shifted, you know, like 2 pi plus, you know, pi divided by 10. What you're going to estimate as the phase shift is pi divided by 10, right? So it moved a lot, but you're going to estimate that it moved very little. And the velocity that you're going to estimate is actually going to be lower than the velocity that you were supposed to be estimating. What does that remind you of?
Aliasing.
Correct. It's aliasing again. It's the same thing that happened with grating lobes, right? And again, this is the nice thing, you know, because you get to see that many of the things that you have been learning, you know, over your many courses kind of come together, right? And keep that in mind. So there's going to be aliasing, and you cannot measure any flow speed with pulse wave Doppler. There are limitations that we're going to clearly describe in our next lecture, because it's already 4:40. And I know that time flies by when you're having fun, but it's time for your quiz of today. Okay, so can you access the quiz? It should be open now. Can you access it?
Yes, teacher.
Yeah.
Yes, teacher.
Awesome. And you will see that today, just for fun, the question of your quiz is one of the questions from the questionnaire that you had to play with. So you have been playing with it, then you have a freebie. And if not, it's okay. It's a doable question that has to do with beamforming. Go at it. If you have questions, just ask away, okay? Go for it.